Yeah, so let's get started, guys. This week we are looking with Nick at the reader component of a chatbot or question answering system. So take it away, Nick. Thanks.
All right. Okay. So yeah, as Chris said, this week's discussion group is just covering some of the research I've been doing on question answering systems, and this week is about the reader component of question answering systems. So in the past couple sessions, we've looked at sort of the overall architecture, and that includes some document source and a reader of that document source, so rather a retriever of that document source that's designed to find the best documents given a question. And now this component is sort of more or less the final component called a reader, which then takes all of the kind of input sequences and information and tries to produce a result. So the input sequences and input information are the question that we ask the system, as well as some of the documents we've retrieved. And so from either one or multiple documents, we want a reader that can take all of the evidence, is sort of the best word for it, and come up with the best answer for our question. And there are two sort of approaches to a reader. These can, of course, be combined given your system, but kind of the two categories of reader are generative and extractive. So extractive, which is we'll do after the generative section, is something that we've covered in the BERT squad tutorial, which was released on the blog a couple weeks ago, but it's a very simple system, and it's a BERT model that's been trained on the squad dataset. And its task is, given a question, to look at a passage. It finds the best span of text within that passage that it thinks answers that question. So this is what's called extractive reading, where you simply are looking for a span, and you're going to extract out of the passage a span of text that the reader believes is the best, most likely answer for your question. And on the other hand, generative readers, these will take all of that evidence, and rather than just looking through one passage or multiple passages and extracting spans of text and, chunking them together or something like that, it takes all of the evidence and it iteratively produces a novel answer. So it is generating token by token or word by word a new answer that might, for example, combine evidence from two different documents. And it is often and can be a piece of text that is not seen anywhere in the documents that it's taking as evidence. So it creates a novel answer, and it's essentially, it's a generative sequence-to-sequence kind of model. So we'll go over those first, and then extractive readers. And then if we have time, I've got a couple notes at the bottom just about looking at all of these different kind of state-of-the-art systems. There are some sort of modifications and combinations of all of the pieces we've seen, and some sort of tips and tricks that really good state-of-the-art systems have tried to use or have used to make their systems just a little bit better. So here we go. Generative readers. The first one we'll look at is BART. And I won't go over it in great detail here, but GPT is a great, if you're not familiar with any of this, GPT is a great kind of, it was very much an early precursor of these autoregressive generators. And autoregressive just means it's going, for our purpose, it means it's going and generating one token at a time. And when it's trying to do this, it's essentially only seeing text in the past. So if we look at GPT here, tokens are predicted autoregressively, meaning GPT can be used for generation. So we're generating one token at a time. However, words can only be conditioned on the leftward content, so it cannot learn bidirectional interactions. So what this means is, say we have the BERT task for say we have the BERT task and we're trying to train a language model. In BERT, as we can see over here, you mask a couple of the words, and then the bidirectional encoder, which is bidirectional is the key word, and that was kind of the motivation for BERT, is to look at, when you're trying to fill in the blanks, being able to look at both the left word and the right word context is really useful. So if you're trying to figure out, if you send into BERT this sentence, A, B, C, D, E, and you've masked out B and D, when you're asking BERT to find out what the masked token was, it's very helpful that the BERT model can see the entire A, C, and E while it's trying to decide B and D. So that was the innovation that was sort of a response to this GPT style. And the GPT style, if it's not really listed here, but if we were to, mask one of these inputs, or if we just want to feed it an initial start token, it generates one token, and then given that token and all of the tokens it's seen in the past, it generates the most likely next token. And then the third step is, given the second token and the first token, what's the most likely third token? So it auto-regressively produces new letters. And this creates a language model where we can generate new words, which is useful if we're trying to generate text, which BERT can't do.
Nick, auto-regressive, that just means like it takes in addition to the input text, the original input, it also takes in like the previously generated tokens. Like those are also factored into the generation.
Yeah, generating left to right. Yeah, this is a very much for our purposes definition, but it captures it. Yeah.
And then with GPT do you remember was the encoder unidirectional as well? I guess
no, I'm not sure. I thought it was. I don't know. I didn't study GPT much, but I thought it was just decoder blocks. No.
Am I thinking? Maybe I'm thinking of GPT-2.
Oh, I mean, they should be the same architecture. So, yeah, if you can speak on the GPT architecture, you might know it better than I.
Yeah. All right. That's okay.
So, yeah, BART is a model that tries to take the best of both of these. So it wants to be a text generation model, which BERT can't do, but it wants to look at its entire, all of the evidence essentially when generating new tokens, which BERT can do. So essentially they take, they feed the sentence through and they take a BERT embedding and they use that in tandem with the regular kind of decoder GPT architecture. I'm not totally sure on what this arrow means. There's some kind of mention of cross-attention, but it's not really totally clear to me without looking at the code what exactly this is. But from a high level, the BERT embedding, which is bidirectional, is just used as evidence to help feed this autoregressive decoder. And the idea is it'll be more accurate if it can see part of BERT, the BERT embedding.
And that's describing the pre-training process, I assume, right? They're doing this masking on the corrupted document, the corrupting input document, but only as a way to pre-train the model.
Yeah.
Okay. All right. Interesting.
And so this model is used essentially as a text generation model. So it's sort of sequence to sequence, and you can put something in and get something out. So it's a good candidate for a generative reader. And it's used by quite a few architectures, including RAG, which we'll get to a little later. T5 is another example. And here it's a little more straightforward, the training method, and it's a sequence-to-sequence model. And it's first trained on a masked training objective. So this is just taking the Common Crawl data set, and we do some kind of mass training objective like BERT. And then after that, it's trained on a series of NLP tasks. And so this is sort of like the second half of its pre-training, after which it's then used to be fine-tuned on something. But the second half is essentially the input like this. It will essentially, in the text, specify the task that it's encoding. So it will, this is the pure text that it's fed. It will say translate English to German, : that is good. And it expects on the other end, das ist gut. So it's sort of trained on like these kind of glue-like tasks. And the idea is that having one model without any kind of extra fine-tuning layers, trained on all of these different tasks, it generates kind of better language comprehension in general. And again, this is a pure text-to-text model. So this is another candidate that's used, and it's particularly effective in a lot of these sort of BART and T5 and not really Fusion-in-decoder. BART and T5 are sort of the most frequently used pure reader models in these kind of very advanced question answering systems. They just tend to have the best scores. That is the motivation.
Do they literally, like, I'm looking at these samples and it says like cola sentence or summarized. Like, is that how they tell the model what the task is?
Yeah.
Wow, cool, okay.
I know. But it's sort of it's interesting to see that that's an effective method, because like I recall I think last week in your multimodal kind of talk, one of the ideas was you just sort of, if you want to feed in a categorical feature to something like BERT, you could maybe just say category 1 : and then put some text in. And it feels very hacky and like it probably wouldn't work, but this is kind of the approach where you just say, this is the sentence I want to translate. And if you do that enough times, eventually it learns that, whenever I see this phrase in the beginning, : sentence, that means I'm looking for grammatical acceptability.
That's amazing.
Yeah. Yeah, and in a bit of some talk where one of the authors was talking about this kind of portion of it, like the STSB sentence, which they're asking for similarity, and it gives a string that is a number between 0 and 5. He was saying, it was sort of remarkable that even after doing it for not that long, whenever you put STSB sentence as a kind of prepend into the input, it wouldn't just, give you something else. It would very, very consistently give you a number between 0 and 5, which is sort of bizarre.
How does it tell the difference between the STS sentence and the thing you're trying to train it? Is it the colon or just figure it out?
Presumably it's the colon. It's just having seen it enough times. It's trained on : sentence, the course is jumping well. And, if it hasn't seen that before, the output will just be, probably random, but then it's punished and told that, I only wanted one of two answers from you, acceptable or not acceptable. So after, this is sort of fine-tuning the model. After a while, it learns : sentence means there's a task coming up and it follows the colon here. Yeah.
Good.
So it's kind of cool, big, all-purpose, general, messy text-to-text model. Okay, so moving on to RAG and Fusion-in-decoder. These are not quite reader models in themselves, but they sort of demonstrate two approaches, and they're very, these systems do very well in question answering, but they sort of demonstrate most of the key ideas about how you include a generator in your model. in your end-to-end model. And that sort of is a nice way to tie in all of the other stuff we've been looking at, because this is sort of close to a final picture. And we'll see a few more of these kind of final picture architectures. But, there are variations in which components are used and how they're arranged. But this is sort of, this is a very widely used one. You can find it on Hugging Face. I think there's even a live demo of RAG on Hugging Face. And as we'll do later, there is a good library called Haystack by DeepSet AI that has a bunch of tutorials on RAG. So if you're interested in trying out like a new, kind of somewhat better, more state-of-the-art question answering system, RAG is a good place to start. But for our purposes, it also ties together a lot of the concepts that we've been talking about and introduces some new ones. So RAG is an end-to-end retriever and generator model. It can be applied like any sequence model with any task that has input and output sequences. But it's really focused on incorporating what's called non-parametric knowledge, which really just means a source of documents or some kind of external source. For the purpose of RAG, that's text documents. And note on parametric and non-parametric, you might see this if you look around. Non-parametric simply means, it's these kind of external documents that are not knowledge that is within the parameters of the model. So an example of parametric knowledge would be something like if you asked a question of BART, for example, it's not trained on this, but it might be able to answer who won the Super Bowl in 2002. It might actually be able to produce the answer. Even though it wasn't trained on that, it's just by virtue of having seen enough Wikipedia articles, and while pre-training, it's seen enough kind of information about Super Bowl 2002 and whoever won that year. And it's seen those together enough that for it, the highest probability answer when you ask it, Super Bowl 2002, is to give the name of that team. So that's sort of parametric knowledge. It's just, it sort of lives within the model, and it's not been specifically encoded, and it's not really, it's pretty opaque. It's just sort of, statistical correspondences it's seen while pre-training. So the focus of RAG and these kind of question answering models is to incorporate non-parametric knowledge, which for question answering systems and in a couple other tasks, it's just much better. It doesn't sort of range across all tasks, but the sort of hope of creating a model that within its parameters knows, knows all there is to know. It doesn't seem to pan out that well. For example, there is a question answering competition called Efficient QA, and in that, the authors are tasked to kind of create the best question answering system they can under a certain size. So they create these systems that might be unlimited or under 6 gigabytes. But these systems, which look something like RAG and incorporate very specifically external documents, outperform GPT-3 on the same task, which is hundreds of times bigger. So this idea that, and this was sort of an experiment of GPT-3, is to see without external knowledge, how good can kind of parametric knowledge be. For most cases, you really need external knowledge. Most likely just because you can't afford hosting GPT-3 or paying for it. It's just not as effective in general. Okay, so the RAG architecture. So we're given a question and a number of reference documents. So the first step is we encode the question, and this would be familiar from our kind of retriever section. We encode the question into a vector, and then we use maximum inner product search against the documents, the document vectors, to find the most similar, the top K documents. Maximum inner product search is just take the dot product, and whichever has the highest, has the closest cosine similarity, that's your top K document. Okay, so then we concatenate the encoded question with the top K documents, and then we feed this to the reader. And there are, for RAG, there's two models, and they sort of greedily, they use essentially beam search to greedily produce the answers. So for RAG sequence, it just takes one of those documents and question pairs at a time and produces token by token, word by word, what the most likely answer is. And then RAG token is their sort of second model, and it sort of looks at all of them in tandem, and so it'll produce one word from one document, and then for the next word, rather than looking at that same document where it thought the answer was most likely to be, it'll again look over all documents and then take the most likely. So conditions on, conditions on the likelihood of the word given the document. It also takes into account the document similarity score to the question. So it's sort of, a heavily conditioned probability generating at each token the answer. The idea is that we've seen some evidence and we've seen our question, and the reader, which is a BART model, is just tasked to create the most likely answer, token by token.
So on this one, when we talk about feeding the documents into the generator, are the documents encoded first, or is the generator somehow like actually receiving the full text of the document?
I'm not totally sure on this, and I even watched an author's talk on what exactly goes on here. So are we feeding each document in, so each question document pair in once, and then asking about that one, or are we feeding them simultaneously? And it appears that the question and the document are encoded. This Z1 seems to indicate that it's encoded before it goes into the generator. But I'm not totally sure. It could be the case that we use the maximum inner product search to find the most likely documents using the document vectors, but then when it's time to go into the generator, because it is a BART model, we would just use the text version of the question and the text paired document and feed that into the generator. But this token case where we feed them all in simultaneously, and then we're conditioning word to word on the most likely next one, it's not totally clear to me. It wasn't clear to me how that works, because if we have 5 documents, then that's 5 kind of question document pairs all being fed into a BERT size model. So yeah, there's some investigation when we're going to create this example eventually for either with Hugging Face or DeepSet. We're going to look at how this is how this step happens specifically.
Yeah, I'm thinking so for BART, it is like a sequence to sequence thing, right? So it takes in text, or I suppose it could take in like a sequence of embedding.
Yeah, but I mean, I think the encoder part is sort of necessary in it.
Yeah.
So if it's just a BART model, it requires the beginning text.
Yeah. So that would kind of imply that, like, maybe once you've done your retriever step, you take like the raw text of the question and add that to the document, the raw document text, and feed that in BART. But man, that sounds like a major sequence length problem.
Exactly. Yeah.
So
how do you put 5 of those in? Yeah.
Yeah.
So I'm not quite sure. And a lot of the sort of the models at the top of the leaderboard, this component is some kind of like Big Bird long former. It's a model that's designed for long sequences.
Oh,
So this maybe indicates that the idea is, and we'll see in Fusion-in-decoder, that the idea is that the more evidence you have going in at once, the better it can be. So it's beneficial to have a generator that can take very long sequences, excuse me. But yeah, it's a little unclear. I don't know how else to do it besides looking at the code, but even for the sequence model, if we're just feeding in one question and one document, it seems like you would just feed it in once to the generator, get an answer, and then the next one get an answer, the next one get an answer, and then you would marginalize over all of those answers, but it's not really specified that that's exactly the way to do it. So
marginalize meaning like pick one of those, pick which one.
Pick the highest likelihood one, yeah.
But then you wouldn't be able to combine knowledge from multiple documents.
That's for the sequence. That's for RAG sequence. RAG token is the one we were talking about where it combines knowledge from all of them simultaneously.
Gotcha. Okay.
Yeah. So RAG sequence is only able to look at one document at a time.
Okay.
And RAG token is presumably looking at all of them kind of simultaneously.
Formulate an answer. Is it going to go from multiple docs? Okay. Cool.
Okay. The final model here is Fusion-in-decoder. And this one came out a couple months ago, and there's a very short paper on Archive. And I include it because it's used in and sort of benchmarks better than RAG, and it's used in a lot of the different architectures for question answering systems. So its performance is very good. Its support is less good. It doesn't exist on Hugging Face. As far as I know, there's only this paper and a Facebook library containing it. So while it's very good, it doesn't have necessarily as good support. And given the short paper, there's also another, I'm sort of unclear about what exactly separates it from RAG, but we can see as we talk through. So the authors, and this is also a Facebook product, so it might just be the same people, and they're not elaborating because they're very familiar with the differences. So after retrieving the top K documents, for each document, the question document are fed through the encoder independently. So this allows one to either pre-encode the passages, and it's implying that in something like RAG, all of these are encoded simultaneously, which is very expensive. So then we take these separately encoded question passage pairs, and we simply concatenate them into a single vector that contains question passage vector here, question passage vector 2 here, question passage vector 3 here. It just concatenates them into one long kind of informative vector. And then this is passed into a decoder, and that generates our answer. So the emphasis here is that the fusion of the evidence only happens in the decoder once, and the documents are encoded separately. So they mark these as the distinguishing factors. And sort of the motivation and what they view as the highlights are, if you can encode these individually, you can essentially pre-encode them, or you can do it much faster, and you can scale it to a much larger number of documents. So the implication is that in something like RAG, when you're encoding documents, you're doing this, the cost is quadratic because you're encoding them all simultaneously, which I don't quite see in the RAG architecture, but they say this is the distinguishing factor. And in the decoder, all of these occur simultaneously, so that helps you make a decision based on the aggregate of all of the evidence. And in some of their studies, the idea is that the more evidence you have, the more passages you can feed in simultaneously, the better the answer is, up to quite a large point. I don't know if they found the drop-off. So it's somewhat simpler than RAG, but it seems to get the best results by a fair margin. So here's Fusion-in-decoder base and large, and natural questions, trivia QA, squad, these are all question answering problems. And so it beats them by a fair margin, particularly on natural questions. And in a lot of the sort of efficient QA competition models and a lot of other state-of-the-art question answering models, Fusion-in-decoder is the sort of key architecture idea used. So, some questions about what separates these and exactly how they work in detail. But the idea is, if you're comparing them, that there's different ways to sort of encode your evidence and different ways to feed that into the decoder. And so this can change depending on your task. It's sort of dependent on the task and what you have available and the costs associated with maybe decoding a very long sequence, trying to aggregate a lot of evidence.
Those scores, Fusion-in-decoder, are really impressive. Like even the base model is outperforming RAG by like a good margin. Seems kind of
yeah. Yeah, compared to RAG, it's doing 10 points better, which is not the in a lot of these papers you're very used to seeing we beat it by 2 points. And it's like,
so we win.
Sure.
Yeah.
But it's, as I was talking about earlier, it outperforms GPT-3 few-shot.
Ooh, yeah.
Which is, few-shot, I think, was defined by them as, 2 or 3 examples go in. But, GPT-3 is an enormous model. Fusion-in-decoder is not that big. So it really is sort of testament to the fact that having non-parametric knowledge and for question answering systems being able to feed in supplemental evidence is really the way to go.
It's interesting that they're reporting all like the EM, I think, is exact match. Whereas there's like another metric they use that gives it a little more flexibility. So I guess exact match seems ideal. I wonder if their edge is smaller though with the looser metric. Where there's some room for getting close to the right answer.
Yeah, that's true. Like maybe it gets the exact match more times, but when it's wrong, it's way wrong. Yeah, this is a possibility. Yeah, I don't know what the sort of standard metric is for these. But yeah, it could be something else. Evaluation of these kind of question answering systems is a topic into itself.
Yeah.
It takes a lot of sitting down and thinking about what do we actually want and how close is close to score these. So.
Hey, Nick, sorry, quick question. What does natural questions mean?
Natural questions is a data set. I believe natural questions is, there's a few, so I might be getting confused, but it's either this or something close to this. Natural questions is a Google data set and I believe the questions are actual user Google search questions. So they're taking, someone has Googled what's the height of, what's the height of Mount St. Helens, or something much more ambiguous often, like who's the best football team. So it takes these questions and creates a subset that it thinks is sort of answerable, and then as supplemental documents, I think it recommends or guarantees that the answer is something in Wikipedia. We can do a quick Google. Yeah, okay, so this is the Google product, and this was used for the efficient QA competition as well. Right. So who is the author of the book Arabian Nights? Short answer, none. Long answer. But yeah, here it's sort of guaranteeing that there's something in the Wikipedia article, which is sort of the non-parametric knowledge that can be used to help answer this question. What does the word China mean in Chinese? Okay. So those wrap up the kind of longer generative readers and the architectures and the ways in which those readers are used.
So John also asked in the chat if there are code implementations of RAG, which sounds like it's in the Transformers library, yeah?
Yeah, there's the original in Facebook's GitHub, and then in the Transformers library, yeah, they've sort of fully supported it. So it's not just a community model. They have full documentation and code examples of RAG for Hugging Face. And I think they had or still have a live demo that uses it, so you can kind of play around with it. So they've done good support on it. And in Haystack, which is the DeepSet AI library, they have it as well. I believe they're mostly pulling from Hugging Face. A lot of that library is built on Hugging Face, but they provide sort of a nice interface. And if you're looking to productionize something or just kind of facilitate using large documents or speed, they kind of have a built-in production pipeline through which you can run this. And they have also good tutorials that are pretty drag and drop. Build your own RAG model. Okay. Now we'll go into extractive reader options. This is a little shorter because most of these kind of follow BERT, which we won't go into in great detail here. We have a couple of blog posts, and there's a lot of information out there about how BERT can be used for span prediction and reading comprehension. So all the extractive reader options just kind of follow this. They just kind of follow, the state-of-the-art ones follow a transformer-based model approach. And the most used one, and for reasons I'm not quite sure of, the most successful one, when this is tested empirically, seems to be Electra for question answering and reading comprehension. So we'll just briefly kind of look at that. And once again, it's very similar to BERT. It's not quite adversarial, which it looks like from generator and discriminator it is. The authors say this is not really adversarial. It simply uses a variation of the masked language close task that something like BERT uses. So the idea here is that instead of just masking a couple words and then asking our transformer-based model to fill in what those words are, we have a generator, which is just a small a language modeling model. It takes a few of those words and replaces them with something it thinks is reasonable. So this is a generative model. And it replaces a couple of those words with either a synonym or something else that is reasonably acceptable. This gets trained along the way, so it gets better at doing this. But then the idea is for the discriminator, rather than to look at just a couple masked words and try and figure out what they are, it has to look at every single word and decide if that word is part of the original text or was replaced by the generator. So the idea is that the authors want it to be a much more efficient training regimen than what's used in BERT, where we're feeding in a whole sentence, but only really training on one or two of those masked words out of the whole sentence. For Electra, we're asking it to train on every single word. So the idea is that it's much more efficient, and in their paper, it's trained in a quarter of the time with a quarter of the compute, something like that, and has quite similar performance to something like Roberta.
I feel like I've always wanted to play with Electra because it did seem like they created a better pre-training task and then kind of showed that like their model is just better than the original BERT at all sizes even. But I've always had trouble getting it to work. I haven't tried in a while. Anyway.
Yeah, I haven't tried it either. And I hadn't really looked at it that often because it does seem, I don't know if it's so much better than something like Roberta that it gets used as heavily. But at least in their experiments and very specifically for question answering systems, it kind of has the best score consistently.
Interesting.
Yeah.
I'm always looking for like the alternative to BERT base, right? like what's better than BERT base?
Roberta, right?
Is Roberta base better? Or
yeah, I think it must.
Like Roberta, Albert, it's like at the large or extra large size, right? They outperform BERT. But at the lower sizes that we tend to play with, they don't actually do as well.
Yeah, I thought Roberta did better because it was just taking better hyperparameters, but I haven't actually looked at it. That was the claim, at least. Yeah.
Okay.
Okay, and that's my very short extractive reader option section. But this really, all of them are some kind of variation of this transformer span prediction. So here is with Electra. When we're done, we just take the discriminator, and it's a language model. And so then we can ask it, given some question, to extract. If we train it on squad, it'll be trained on span prediction, essentially. Okay, we're coming up on time, so I'll just briefly go through, and you can look at this on your own. I've just sort of nodded towards these, but these are some of the leaderboard systems. And again, the idea here is that there are if you were tasked with building your own question answering system, you would have, in production, you would see all kinds of problems and you would have all kinds of solutions or, unique issues that you would want to resolve. And some of these kind of incorporate ideas where that is the case. So for example, reflection net, and I've picked these just because they're in the top of the leaderboard in something like natural questions or other question answering systems. Essentially, it's not so different, but they've added the key idea is a reflection model, which asks, say we have RAG end-to-end, and it produces some answer. The idea of the reflection model is to include sort of a confidence model at the very end of our RAG output. So it will then look at the RAG output and say, this is what RAG thought was the most likely answer. Was it actually any good? Because sometimes a question is asked for which there's no evidence or there's no answer. So it might be, a question that inherently has no answer, or the question doesn't have any support or evidence documents in the database. So sometimes, even if you play with our BERT squad model released a while ago, if you ask it a question for which it has no evidence, it'll give you an answer no matter what. But it might be the case that that answer is quite wrong. But the BERT squad model itself doesn't have a way of recognizing or saying this is really low confidence. So this is kind of like, if you were putting this in production, you would want something like a reflection model maybe that says, yes, this is the most likely answer, but it's not likely enough to be a good answer. So instead, we're going to output, question not found, or, answer not found. And so this kind of innovation on a more or less familiar architecture leads to better results. And as discussed a little bit earlier, other models at the top of these leaderboards are pooling former and cluster former, and essentially their innovations very much like BERT. So for the generator portion, we're essentially just using something that's very good at handling long sequences. And so both of these are kind of innovations on reducing the computational and memory cost of computing the attention matrix. So the idea is here, and which was sort of discussed in Fusion-in-decoder, is that the more evidence you have and the longer your sequence can be, and being able to attend over a very long sequence and recognize at the beginning of the sequence and the end that these two things are connected, that proves very important in certain types of question answering. So the fact that at the top of the leaderboard are these generator models that are focused on being able to handle long sequences of text is just sort of an indication of that. And then very briefly, a few kind of variations and tricks that were seen in the efficient QA competition. So these were submissions to the natural questions dataset, and it was a Jeopardy dataset. But essentially the task was create the best possible question answering system that would look at something like Wikipedia and answer questions. And so in here, and I've included a YouTube video that has the winners sort of talk through their solution briefly, as well as a report on, the whole competition and details of the winning models. There's just a few kind of ideas here that if you are building one of these systems, you would probably end up playing with. So one kind of obvious one is combining extractive and generative readers. And maybe that means, as in here, you take the passages and you pull out the spans with an extractive reader, and then you feed those most likely spans into a generative reader, and then you produce an answer. And another might be to take answers from an extractive reader and from a generative reader and feed those up into a kind of ranking system and ask it to then predict the best answer. And this idea of kind of re-ranking models or re-ranking functions occurs a lot, where you might retrieve passages and then you'll want to re-rank them based on some other criteria. So like at any stage, kind of reevaluating what answers you've produced, maybe using new or old knowledge, was kind of a popular idea in all of these systems that eked out a little more performance. And then, of course, for the retriever and the generator, there's different ideas about maybe how you would take that and you would continue training it or sort of fine-tuning it on your objective. And so in this competition, they tried a lot of different training objectives, different loss functions to try and get their individual components as well suited to the final task as possible. So all of these, the sort of main theme is about combining different components, taking those components maybe off the shelf and fine-tuning them for your application very specifically. And if you're building a question answering system, that's kind of what you want to do. You want to be tinkering with each of these components and the architecture as a whole to try and get the best performance for your task. So it will look, it wouldn't be surprising if your optimal model doesn't look like RAG, but it looks something kind of Frankensteinish like this, where you're just pulling in different parts. And hopefully that's kind of the idea you've gathered over, these talks is it's less about one specific model because there will always be a new model, there will always be a new system. It's about kind of understanding the core components and how they fit together and variations on those core components and how you might have some intuition about which ones are best for your system. So we're very close to time. That took way longer than I thought, so we'll...
I interjected a ton of questions in there. With this last section, would you say, are these kind of, it's like if you look at a Kaggle competition, right? If you want to actually win, there's always lots of crazy little tweaks made to just kind of edge up over the competition.
Yes.
Is that kind of what this is versus significant gains?
Yeah. It's a lot of little innovations, or we did this fine-tuning task with our generator before putting it in the system that got us a couple points higher. We tried out these different retrievers, and we retrained our retriever a couple times on this different data set, and that tended to help it. So it's a lot of these little tiny components. But yeah, it's kind of like the Kaggle competition where people are incorporating different little tweaks to try and eke out more performance.
Any other questions? I'm hoping, I feel like we had a lot of questions in here. I'm hoping some people watching the YouTube video will help us out.
That would be ideal, yeah. If someone could say, I know exactly how RAG works.
Right.
Vector X goes in here, yeah.
If not, we'll go figure it out.
Yeah.
Man. Yeah, what are you most interested in looking at here, Nick? What would you say seems worth digging into more?
I think I think we want to make a RAG, a more detailed RAG kind of tutorial because it seems to do pretty well and it's well supported, so it's probably just the most obvious application that people will be able to use and play with. So I think providing more detail around RAG would be good. And then, possibly after that, doing some kind of picking some task and trying to make the best kind of very custom question answering system would be good because you could share the model itself with people and hopefully they can plug in their own data set and try it out. And we'll have some more kind of learnings from trying to build one ourselves and sort of the problems we ran into and the things we tried. So I think all of this would be kind of helpful to share.
That'd be cool. Did you get the sense from the, so you said Fusion-in-decoder came out of Facebook. Is their model published at least, or is it one of those models where it's we're keeping this one to ourselves?
I don't think it's that. I think it's published. I think it's just so recent, 2 months ago, that they haven't created quite enough support for it.
I remember when we first started looking at this question answering stuff, It's a while back now, right? Like 6 months or more.
Yeah.
But you had tried RAG because RAG was in Transformers, but it didn't really work out of the box, right? It's like,
No, and I'm assuming they've fixed it, but they had some examples to run. Yeah, and it was not compliant. I had to basically rewrite their modeling source code, and yeah, it's
always tough to deal with that there's it's like, this is really promising right now, it doesn't work, but
yeah, and I think it's very good. This was like 2 weeks after they had released it, an initial release, so I don't really assign any fault to them for not having their third fine-tuning script, completely worked out. So, yeah.
All right. Well, I think if there's no other questions, we'll wrap it up there. Thank you, guys. Next week, I'm going to talk more about combining categorical and numerical features into BERT. So we're going to kind of hop back and forth between those two topics. So hope you guys can join next week.
Sounds great. So, great presentation. Thanks, Nick. Thanks, Chris. Really appreciate it.
Yeah, thanks everyone for joining.
See you guys.